So we have some experience thinking about this partition function and using it to calculate the probability and the average energy in a two-state system. So that was the simple example we just worked out. Now I want to kind of generalize that a little bit to see what else this partition function is good for. And that is for calculating thermodynamical quantities. So all of the things we learned from earlier in the course, you can find them from the partition function. So the partition function is really the most important function in statistical mechanics and in thermodynamics because you can learn all kinds of things about the system if you know the partition function. So as an example, I want to focus here on the average energy. So suppose you have a system and you want to know the average energy of the system. Now I have to generalize a little bit because let's say we have a system of n particles. So I'm going to have bunches of particles, okay? And you can still write down a partition function because I could have states of the system. You know, I could have one particle here, one particle here. That's one state. This is, this is another state with them like this. So I can still write down a partition function for all of these different states, even if I have multiple particles. And then the average energy of the system is what we've been calling U, the internal energy. So this is the internal energy of the system, or the thermal energy of the system. That's the average energy of a system of n particles. And what I want to show is that you can calculate this internal energy from the partition function just by doing some calculus. So let's take U. I'm going to take this formula up here, and I'm replacing E bar with U. So E bar is the average energy, but that's what we're calling the internal energy. So U is sum over all states. So sum over I is denoting the state. And then EI, the energy of that state, e to the minus EI over kBT. Okay. And then, sorry, I forgot I 1 over Z out in front here because this probability here has a 1 over Z in it here. And I can pull the Z outside of the sum because Z is independent of I, right? Okay. In order to go further than this, I'm going to pull a trick. So let me show you a trick here. And the trick is to recognize the following thing. If I take the derivative with respect to t of e to the minus ei over kBt, what do I have? It's e to the minus ei over kBt times the chain rule, the derivative of the exponent, which is minus ei over kBt. And it's a derivative with respect to temperature, so the ei comes out front. So I got minus ei, e to the minus ei over kBt. And then I've got derivative of 1 over t, so I get minus 1 over kb t squared. So that's a derivative with the chain rule. Okay, there's two minuses here that cancel out. So this minus cancels with that minus. And what I get is, let me simplify it a little bit, I get ei over kBt squared times e to the minus ei over kBt. Okay. And let me put the kt on the other side, kBt squared, times the derivative of e to the minus ei over kBt is equal to ei, e to the minus ei over kBt. Whoops. Okay, why did I do that? Because this thing here in the sum, ei, e to the minus ei over kt, is exactly this. And what I just showed is that you can write that in terms of the derivative, which is shown here. And so we're going to use that. On the next slide, I'll substitute in this purple thing here in this sum with the red thing. Okay, so let's go to the next slide and we'll finish that up. Okay, so this was our formula for the internal energy of the system. The sum here was over all states. And on the last slide, we showed that this could also be written in terms of a derivative. So let me substitute in that derivative. It looks like this: kBt squared d by dt e to the minus ei over kBt. Okay, now to go further, think about, remember this sum here is over I. So things that don't depend on I can bring outside of the sum. So I can bring outside this kBt squared, and I can also bring outside the derivative, because the derivative of the sum is the sum of the derivatives. Derivative is a linear operator. So I can bring those out. I get 1 over z, bringing outside kBt squared and the derivative, d by dt, sum over I, e to the minus ei over kBt. And then what you notice, this sum again is over all states, is that this thing here is exactly the partition function. That is this. So this is z. So I have this kind of nice prescription here. If I want to calculate the energy of the system, the internal energy, and I know the partition function, all I have to do is take a derivative of it. So I have kBt squared d by dt of z, just like that. So it's really nice and simple. It shows us that if I know z, I take a derivative of it and then I multiply by this thing out in front here, and I get the total internal energy of the system. So that's a really nice way to calculate a thermodynamic quantity, which is the internal energy of the system, just by taking the derivative of the partition function. And this is a general thing that we're going to keep seeing over and over again, that we're going to be able to get a lot of thermodynamic quantities from the partition function. That's why this partition function is so useful. Okay, so continuing along this line of calculating thermodynamic quantities from the partition function, the next thing I want to think about is, how about entropy? So how can I get the entropy of a system if I know the partition function? And there's a way, and we're going to figure out what that is. So the first thing to do before it's going to seem like it comes out of left field, and it does a little bit, but I'm going to define some quantity, F, and F is called the Helmholtz free energy, and it's going to be defined as U minus Ts. So this is called the Helmholtz free energy. And if I had more time, I could talk about the physical significance of it, but for now it's just a useful trick, a useful function, and you'll see why. Let's think about what is dF. Let's use our differentials here. du minus TdS minus S dt. So I took a differential of both sides. And then I use the combined first and second laws, right, of thermo, which told us that du was dq, which is TdS, minus dw, which is PdV. And so I'm going to remove du minus TdS is equal to minus PdV. And so I'll substitute that in here. So du minus TdS, that's equal to minus PdV. So I get dF is equal to minus PdV minus S dt. Okay. And now remember if f is a state variable, and it has to be because it depends only on other state variables, that I can read off the partial derivatives by comparing it with the general formula for an exact differential. So the two variables that are showing up here are v and t. So if I think of my function f this free energy is a function of v and t, then its differential df has this form. So partial f partial v with respect keeping t constant times dv plus partial f partial t keeping v constant times dt. And I can read off from here that minus p is equal to df dv at constant t. So that comes from comparing this coefficient here with this coefficient, and then comparing, let's see, I need yet another color, this coefficient here with this coefficient. So minus p is df dv at constant t, and minus s is equal to df dt at constant v. Okay, so what does this tell us? It tells us that if I know f, this thing called the Helmholtz free energy, I can get both s and p by taking derivatives. So that seems kind of useful. And now what I have to prove to you still is that f is related to the partition function. So if I can determine how f is related to z, then I'll be able, if I know z, I'll be able to determine f, and then f can tell me pressure and entropy. Okay, so that's the next step, is to figure out how is f related to z, the partition function. Okay, so I've tried to summarize all the things that we've defined so far. So we're trying to determine how to get the entropy of a system if I know the partition function. And what I've done is I've written just a summary. This was if I knew the partition function in a way I could get the energy, the internal energy of the system. And then I defined this quantity called F, which is called the free energy, which had this definition. And then on the previous slide, I showed that if I knew F, I could get the entropy by taking this derivative. Now, my goal here is to show how F is related to Z. So that way I could get entropy if I knew Z. And I'm going to claim that F is equal to minus kBt natural log of Z. Okay. Okay. And now let me try to prove it. I'm going to show that this is consistent with above. In particular, I've got two expressions for S. I've got the entropy here and I've got the entropy here. So those two have to be consistent with each other. So let me show if I write S in those two forms, I have an equation involving F, which has to be satisfied. Okay, so I've got two equations here. One, if I solve equation 1 for entropy S, I get this. S is U minus F over T. And then I've got another equation here, which involves S, which is this one. S is equal to minus df dt at constant V. So those are two different equations for S. They have to be, both have to be true, so they have to be equal to each other. So now let me show, I'm going to show that this equality is satisfied if F is equal to kBt log Z. Okay, so by doing that, in order to do that, I'm going to take this derivative, df dt at constant V with a minus sign. What is that? Okay, so I just substituted in for V, for F. There's no V's here, so I don't need to worry about keeping V constant because V doesn't appear anywhere, so that's good. The minus signs cancel out, and I've got two terms from a product rule. The first term in the product rule is the derivative of T, so I get Kb natural log of Z. The second term in the product rule is plus Kbt times the derivative, d by dt, of log of Z. And let me write this again. kbt, and I'm going to write this in a more suggestive form. Derivative of the natural log of z, that's 1 over z, times the derivative of the inside from the chain rule, which is dz dt. And now stare at this and you can kind of identify a few things. This one here, kb log z, looks a lot like f here, except there's a minus sign and there's a factor of t missing. So this is equal to minus f over t. And this thing here, kbt dz dt over z, that's almost exactly the same as what we have up here for u, except there's a t missing. So this is equal to u over t. Whoops. So what I showed is that df, minus, let me write it down here, minus df dt at constant v, I showed that if f has this definition, that df dt at constant v is equal to u minus f over t. And that's exactly what this says here, right? So I showed that if f has this definition, then the equations above are it's consistent with the equations for above, so hopefully it convinces you that this is the right definition of f. So the math gets a little bit complicated, but it's worth summarizing because it's so important that if you know this partition function, you can get all kinds of things about the system. So if I know the partition function, I can determine the internal energy U. I can also determine this thing called the free energy F, which is kBt natural log of Z with a minus sign. And then once I know that, I can determine both the pressure and the entropy just by taking derivatives. So that's really, really amazing that you can get all of that thermodynamic information from one function, just from knowing the partition function. So that's why this thing is the most important quantity in statistical mechanics, because it tells you basically everything about the system. So to go forward, maybe I'll do a quick example of using this, and then we'll finish this topic.